A very good morning. I bid to Dr. Chu and Dr. Rajasekhar. We are from Group 15 and we have worked on Title 2 Plant Design for Offshore LNG as per our requirement for PDP1 with the supervision and guidance of Dr. Chu. The outline of our presentation today is as follows. And now I will begin with Chapter 1 Introduction. The main focus of this project is the conversion of natural gas to liquefied form of natural gas and the purification. Firstly, looking at the conversion which is being highlighted now in the background of project is this process is a low temperature refrigeration, also known as liquefaction, which occurs at negative 160 degrees Celsius at atmospheric pressure. The purpose of converting natural gas to LNG is because LNG is a more easily transportable liquid because of its volume of approximately 600 times lesser than natural gas. Hence, it is more economical to transport liquefied natural gas across the ocean through ship instead of using pipelines for natural gas. And now looking at the purification process, this is required because of the large amount of contaminants such as H2S and CO2, which is found at the wellhead of natural gas. These contaminants are known to be harmful and corrosive and requires a processing system to eliminate them. Thus, an optimized technology is to be identified for this both liquefaction and removal of contaminants process. This soot floating plant should also cover several other aspects such as by taking into consideration such as to maximize the hydrocarbon recovery, to minimize the energy consumption, and taking into account of the safety and environmental concern by also complying to the HSE guidelines. As stated earlier, the economical feasibility has been highlighted because natural gas is not economical feasible to be transported. And initially, when natural gas is found at the wellhead, it also contains other hydrocarbons such as ethane, propane coming together with all the other impurities. So it is essential to treat all these other contaminants, as improper discharge of it may lead to damage of processing equipment and also can cause harm to the environment if it is released to the atmosphere. To be more precise, for instance, CO2 which is saturated with water could lead to damage of processing equipment. This is because it is highly corrosive, especially when it is saturated with water. It could also decrease the heating value, resulting to solidification in chillers or refrigerants. Next, upon the mercury as a contaminant is a highly toxic contaminant, and that is why usually it is treated prior to other contaminants. And natural gas with hydrogen sulfide could acidify water and cause corrosion, especially the transporting pipelines as it's always intact with it. And with all this damage of equipment caused by the contaminants, it could lead to the entire failure of the engineering system, resulting to a huge loss for the plant. Thus, predominantly as a preventive maintenance for equipment and consideration in other aspects as highlighted earlier, all these contaminants are supposed to be removed and natural gas is supposed to be converted to LNG, the objective. The impurities level should meet the LNG product specification and fulfill the environmental performance standard. With this, we will be able to produce a high quality gas stream product with minimal energy consumption. And this would, so a good purification and conversion process can be designed.
Hi, my name is Ng Hao Kit and I will be presenting for Chapter 2 Literature Review. First, I would like to talk about the primary energy supply of Malaysia in 2015. From the chart, it is clear that the majority of the supply comes from natural gas. Furthermore, the market for natural gas in Malaysia increases as countries such as Korea, Japan and Taiwan import natural gas from us. According to a forecast, the market demand of natural gas is expected to grow until 2030. However, due to the recent COVID-19 breakout, numbers are expected to drop. Next, I would like to talk about the properties of natural gas. The difference in boiling point is important especially for liquefaction, as hydrocarbons such as methane, ethane, and propane are separated by the difference of boiling point. Next, I would like to elaborate on natural gas characteristics. To remain the standard of LNG production, Malaysia ensured that its retail quality of premium sweet liquefied natural gas to contain at least above 90% of methane content, carbon dioxide content lower than 5%, as well as having less than 2% of sulfur. With higher quality of LNG, Malaysia was able to expand its market by exporting to other countries. Based on the graph, we could see an increase in the export of LNG each year, and at the same time, LNG was imported into Malaysia since 2012. This is done to maximize revenue, as lower quality natural gas was imported to cater the Malaysian market, while exporting higher quality natural gas to other countries. Next on the list, the selection of plant location. The study was conducted based on raw material availability, climate suitability, transport facilities, labor supply, and site characteristics such as depth of water. And based on these criteria, Kanowit, Sarawak was chosen as it carries higher weightage than the other selection. Before proceeding to Chapter 3, I would like to compare the different acid gas removal mechanism. The technology chosen here was membrane acid gas removal. This is because it has a more compact footprint and low weight.
Now for Chapter 3, Conceptual Design, let's begin with the optimization of equipment. Generally, the process begins with mercury removal unit, followed by dehydration unit, acid gas removal unit, extraction, and ends with the liquefaction process. For the optimization of equipment, we have selected one of the separation unit, which is AGRU, and the selected technology for this after evaluation is the membrane technology. This technology allows selective removal of fast gases such as CO2 and H2S as permeate when it dissolves through the membrane, and the other slow gases becomes the retentate. The differential pressure between the retentate and permeate induces the separation. Some hydrocarbon gas which has permeability close to the acid gas will be lost, and that is why it's important for us to have high selectivity, thus low amount of hydrocarbon will be lost. And next, it's important to have a permeability which is high because a low membrane area will be required, which reduces the cost. As we can see, there are three different parameters which can influence the selectivity and permeability of membrane. And these parameters can be played accordingly to get the desired and optimized value. Moving on to the process screening, two different sequence has been proposed for the NGL fractionation. The objective of this process is to reclaim the individual fractions of the natural gas liquid using individual columns or distillation columns. So we have selected sequence 1, and this is because component A, which is the lighter fraction, comes out as the top product, whereas the heavier components comes out as the bottom product, component B and C, the ethane and propane. And for our first column, it should be selected the one with maximum driving force of largest value. This is because this would ease the process of separation. It is easier to separate methane as its boiling point is significantly there is significant difference in the boiling point of methane compared to ethane and propane. Due to the huge temperature difference, the separation of methane is easier because low energy requirement is required, and the cost of equipment is reduced as well. In addition to that, the quantity of methane, the amount of component A, the methane, is higher compared to B and C, which is the ethane and propane, which is another additional factor which eases the separation process.
Hi, I'm Safwana, and I will be presenting about the manual calculation of material balances. An example of manual calculations of material balances that I'm going to present is the at mercury removal unit, MRU. To begin with the calculation, we assume that the efficiency removal of mercury is 98.68%, where we obtain from a literature, and after that we calculated the flow rate of each component. For example, here we calculated the inlet flow rate of mercury by multiplying total inlet flow rate with the weight fraction of mercury, and after that we continue with to calculate the flow rate of outlet flow rate of mercury by multiplying inlet flow rate of mercury times with 1 minus the efficiency removal of mercury. Since MRU only remove mercury, and therefore only the outlet flow rate of mercury change, and the other components remain the same.
Next, I would like to elaborate on the economic potential of the plant. The profit and cost of products, byproducts, and raw materials are listed in Table 9, Annual Revenue of Products and Costs of Raw Materials, while Table 10 shows the maintenance costs required per year of an offshore plant. As stated in the report, 12% of the gas extracted was used as fuel gas to reduce the cost of utilities. To compare with a diesel generator, an approximate of 69 million USD worth of natural gas is used as fuel, while a diesel generator would cost billions of USD to generate electricity. Next, the table compares the total duty of heater and coolers of the plant before and after heat integration. An approximate of 455 million US dollars worth of diesel was saved when heat exchangers are introduced into the system. Last but not least, with an estimated revenue of 196.688 million USD per year, an estimation of 4 years is required to pay off the 650 million USD one-off drilling costs of the well. Now, I would like to talk about the simulation model. Based on the given topic, a few assumptions was made for this simulation. Since raw natural gas is saturated with water, water drive technique is used to recover gas from the well. This technique requires higher operating pressure to recover 50% of the gas from the well. To avoid unnecessary rusting of equipment, mercury was first separated by using a flash. This was done when raw natural gas is cooled and flushed in a phase separator. After the removal of heavy metals, triethylene glycol was used to flush out excess moisture in the stream. Triethylene glycol was then recovered and introduced back as inlet of the absorption column. Then, the stream is passed through a high-efficiency membrane to remove acid gas, which consists of carbon dioxide and hydrogen sulfide. Now, the stream is ready for liquefaction. Methane was first separated by using a demethanizer. This is because separating a bigger chunk from the stream is more effective than separating it later. Ethane and propane was also fractionated to be sold separately to increase revenue.
Hi, so this is our PFD before heat integration. We drew our PFD by using visual software. So this PFD tells that this section covers the MRU process unit. This section covers the dehydration unit, and this section it covers the NGL extraction, and the top one here it covers the liquefaction process unit. And towards the end of my presentation, I will show the PFD after heat integration. So to begin with heat integration, firstly we identified the stream data by extracting the info from our process flow sheeting. And from this stream table, we can see that there are 2 hot streams and 1 cold stream. And the data that we extracted include the supply temperature, targeted temperature, and also heat capacity. And based on this info, we can actually calculate the heat duty of the process by using this formula. And in order to proceed with the next step, we actually need to set a minimum temperature difference, and as we actually set our minimum temperature difference as 10 degrees C, which is based on literature, as it stated that an LNG process can be categorized as petrochemical. In order to determine maximum energy recovery, actually there are 2 ways to determine it. The first one is by problem table algorithm, PTA, and another one is composite curve. And for PTA, the temperature will be shifted by using this formula, and then the shifted temperature will be arranged from the highest to the lowest, as shown over here. And then the temperature difference and heat capacity have to be calculated in order to find the heat duty for every temperature difference. And after that, after calculating all those heat duty for each temperature difference, we proceed with heat cascade. Here, the heat cascade is generated by using Hill software. From this heat cascade, it can actually tell us the minimum duty for hot utilities, which is at the top here, and then at the bottom here is the minimum duty for cold utility. And also from heat cascade, we can also determine the pinch temperature, where the heat duty is equal to 0 kilowatts. And from this pinch temperature, we can also calculate the T pinch hot and T pinch cold by using these 2 formula. Right. From the composite curve and also GCC, grand composite curve, generated from him, we can actually here we can also find can determine the minimum duty for both hot and cold utilities, and as well as the pinch temperature. For example, here the minimum heat duty for hot utilities is equal to 6.55 times 10 to the power of 5 kilowatts, and for QC min equals to 7.48 times 10 to the power of 6 kilowatts. Okay. Now moving on to the next slide. In designing heat exchanger network, there are several pinch rules that must be obeyed, and those rules consist of heat capacity, number of streams, placement of utilities, heat transfer, and also temperature difference as shown in this table. And then by obeying the pinch rule, our heat exchanger network that we got is there are two coolers. There are two coolers at the below pinch, and one heat exchanger also below pinch, and one heater above pinch. Okay, from the simulation we did in the HIN software that I just explained just now, we can conclude that by applying the heat integration, we can the consumption for both hot and cold utilities can be reduced in the chemical process plant. For example, here hot utilities is reduced to 6 from this value to this value, and also cold utilities we managed to reduce it to 7.49 times 10 to the power of 6, and overall the utilities can be saved up to 13.93%. So after incorporating in the previous PFD, the new PFD appears as shown. With this, I pass my presentation to my friend. Thank you.
Hi, my name is Maisara. Okay, process instrumentation and control is necessary to be used to maintain the process performance and efficiency. Okay, brief introduction. Instrumentation is used to monitor and control the operating conditions of the facility. It can be categorized under two main functions. The first one, input devices, which are the measuring instruments, measures different process variables such as pressure, temperature, flow level. Okay, the second is output devices of the control system, which are called the final control elements. So here represents the control loop of a system. The sensor measures the process variable from the process flow, and the transmitter sends the information to the DCS controller located in the control room. And then the controller checks if the process variable agrees with the set point. If not, it will send corrective signal to the control valve. That will make adjustment in the process flow to match the process variable to that set point. Okay. Okay. Here's are the control strategies for plant. This is for distillation column. Mostly we use feedback controller. Okay. Distillation column is used to separate mixture of solutions with different boiling points. In our offshore LNG plant, distillation column is used in the fractionation process for extraction of methane, ethane, and propane. Okay, let's look at the first one. The first control variable is the pressure. Okay, the pressure is maintained by manipulating the cooling water supply flow rate to the condenser. Okay, the pressure of the condenser will increase as the liquid vapors produced in the distillation column increases. So the cooling water flow rate will be adjusted in order to condense the vapors. Then pressure will be reduced back to the desired set point. Okay, next the liquid level in the distillation column will be maintained. Okay, the flow rate of feed stream will be adjusted to ensure the liquid level is maintained at the target level. and prevent from liquid overflow in the column. Okay, the similar mechanism is applied for maintaining the liquid level in the reflux drum and the reboiler. Okay, next, the control strategies for another equipment, which is absorber. Um, okay, okay, the flow rate of TEG is controlled to ensure the performance is maximized and efficiency of absorber is enhanced in the DU system. The pressure in the absorber will be controlled by control valve at the outlet of gas stream. The control valve will be varied and manipulated as to control the pressure in the absorber. And then the liquid level is also controlled in the absorber to ensure the efficiency of absorption process occurs in the absorber and also to prevent overflow. The control valve at outlet stream of TEG with water loading will be manipulated in order to maintain the liquid level in the absorber. Hi, my name is Maisara. So our project also covered HAZOP as part of process safety. Here's a brief introduction of HAZOP. It is a risk management technique used to identify potential hazards and flaws from the design and operation that can deviate from its original intention. Who conducted the HAZOP? It is performed by a team of experts with experience, knowledge, and have understanding on their part of the system. When HAZOP is done, it is carried out in the preliminary phase before any new plants are commissioned or in any operational phase if any equipment or process is changed. Okay, why HAZOP? Because HAZOP study could have exposed flaws in the design and prevented undesired incident from happening. Okay, how actually HAZOP is conducted? HAZOP study uses guide words to systematically determine possible failures that could result from operation of equipment outside of design conditions. So this outside of design condition can occur due to possible maloperation or malfunction of individual items of the equipment. Okay, then a list of necessary actions and recommendations to improve the safety and mitigate consequences of hazards will be prepared in the form of hazard report. So this is one of the examples of hazard assessment for our project where I choose the node at C401 demethanizer column where the design intends to separate methane from other heavy hydrocarbons. I choose this study node as an example because many process parameters that is relevant to the equipment's operation can be seen here such as temperature, pressure, flow level. Okay, so for the deviation identified for each process parameters, what are all the possible causes? What will be the consequences? What will be the safeguard? For what are the recommendations? Okay, let us first identify the first cause, which can result if more flow to enter the column. There could be a possibility of control valve failures or flow controller fault to detect the increased flow rate. This lead to rise in liquid level within the column or eventually flooding in the column. Okay, the recommendation, we could install high level alarm or check the maintenance procedure and schedule. Okay, next, what if less flow going into the column? Okay, it may be the possible cause may be because of control valve failures or blockage involved at feed line or pipe falling or leakage somewhere in the upstream feed line that lead to separation fail to take place because of column drying out or feed accumulation in the piping leads to pipe burst because of pressure building. So the recommendation also the same, we can install low level alarm or check the maintenance procedure and schedule. Okay,
The objective of the project to design a potential offshore LNG plant with conceptual process design to meet the market demand and to remove the contaminants H2S and CO2 which are largely present has been done. And based on the evaluation, the selected technology for acid gas removal is membrane permeation. due to its advantages, such as that it requires smaller area and does not require manpower to operate it at all times. Coming to the location, Canary Sarawak was selected mainly due to the large amount of natural gas present there, and also considering its site location, low wave height, and dense population for labor supply. The plant's economical feasibility study was carried out by performing economical calculation by considering the raw material solvents such as triethylene glycol, which is used, and the utilities for plant operation, and a revenue of $196.688 million per year has been roughly estimated. After that, heat integration was performed using Haynes software to save the cost of utility by maximizing energy recovery and to avoid the wastage of energy. After performing HINT, the utility saved is 13.93%, with 2 coolers placed below the pinch, 1 heater above the pinch, and 1 heat exchanger below the pinch. The control strategy, which is mainly used for the process unit, is the feedback control. And lastly, when hazard analysis was performed, this is for the safety of the plant to come up with a viable and economical natural gas offshore platform.